Right, so my name is Claes Redestad. I'm here to talk about string concatenation again, following up some pretty interesting talks on Babylon and such, with going down a little bit more into a JDK library thing that we've been working on. So I'm a member of staff at Oracle, and I've been working on performance stuff for 11, 12 years now, mostly doing benchmarking and helping out with the various features to do them. One of the things that I started working out quite some years ago was the in-defined string concatenation JEP that went into JDK 9. JEP 280 set about to change how string concatenation is translated by Java-C from the traditional bytecode sequence of string builder append chains into using an invoke dynamic to defer or delegate how to translate string concatenations to the runtime, to the JDK core library. This was, of course, motivated by performance. The default strategy that we do today or provide today in the JDK often delivers up to 2-3 times better performance compared to the JDK string builder baseline. And the allocation rate is often half that of Java 8. But the JEP 280 has turned into a series of challenges in recent years. From the get-go, we had challenges with the startup and footprint overhead. Rather than just loading some bytecode string builder append chains, we go into and generate code, which brings, accumulates milliseconds on Bootstrap. And on the far end of the scale, the default strategy creates complex expressions that turned out to be a little bit of a mouthful for the JIT to consume at the upper end of the scale when you go into expressions with 40, 60, 80 arguments. The expression tree that builds up becomes a mouthful for the JIT. We had a bug recently where C2 the C2 JIT uses up to 2 gigabytes of resources to compile. It would use more, but it crashes once it gets even more complex. So we revived a little bit of a workaround to produce a strategy that produces simpler shapes, like one class per such complex string concatenation expression. This was recently added in Java 23, and you can control which arity of expressions will use this workaround. But the workaround, while having certain benefits, it starts up faster, warms up faster. For an individual concatenation expression, it usually performs worse, and it scales poorly on large applications, since you will have one class generated per string concatenation expression in your entire code base. So if you have 10,000 string concatenations, you will get an extra overhead of 10,000 classes. And many code bases we've seen have even more string concatenations going on. So these challenges led me to send in a proposal for this talk to see if we can prototype something better. So this workaround we did just a few months ago, when we figured that maybe there's a room for improvement here and time to rethink this. But the current implementation, we have to start somewhere. So let's look at where we are and where we came from. So when we have string concatenation expressions in Java 8, that would translate into a pretty straightforward sequence of create the string builder, put any constants on the stack, append them one by one, and and then finally do the toString on the string builder and return that. The Java 9 and for our YEP 280 sequence that we've done ever since is basically just put the argument on the stack and then the invoke dynamic to some magic place in a library function. In this case, the make concat with constants in string concat factory. So then in the bytecode or in the class file, the recipe which includes the hello string is part of the argument to that bootstrap method. I'm not sure how much detail I'm going to go into with the invoke dynamic and method handles, but let's do a quick rundown at least of what's going on when you see a invoke dynamic. So the first time it's seen and or executed, it calls into the bootstrap method that is declared in the class file. So in this case, you go into the make concat with constant, and that will return a call site. The call site has a method handle, and when the call site has been installed, you will execute the invoke dynamics as if you were having a target method handle, and you would invoke that exact with the arguments on the stack, and it would return whatever the bootstrap method type says. So it's a little bit of a parlor trick to change and delegate, but it's well very flexible, and what the bootstrap method does with the information can vary, which is one of the motivating things for YEP 280. We delegate, depending on what you're aiming for. You could have tuning flags that says, just give me something quick and easy that doesn't optimize too well, or we could specialize and give us something that might have a little bit more of a startup footprint overhead or whatever. But that's it. And then to complete that crash course picture, we also need to understand and know what method handles are. And method handles is this very flexible API to basically reflect and get executable references to some code. And the method handle can be a very direct reference to method, plain reflection, but it can also be either one of some primitive intrinsic method handles that are available in the method handles API, or it can be something that is composed of other method handles. You can filter arguments on a method handle by applying a filter, and then you get a new method handle that takes these two method handles. You can bind in arguments so that you have something that refers to a static methods, and then you bind in the first argument, and now you have a method handle that kind of hides away that first argument in a bound method handle, and so on and so on. And this relates to the string concat factory because we, in the current strategy, basically takes direct method handles to a set of very simple methods like initial coder, mix, new array, prepend, and new string, and compose these using the depending on the shape of the concatenation expression that we want to create. So we take these method handles and do a very convoluted and backwards chain of method handle transforms. The code to produce method handles usually becomes a little bit hard to read because it's usually since what you invoke is the last thing you create, it kind of inverts the control flow based on our natural understanding of program flow. So we start from the bottom and filter in arguments. In the string concat factory, we filter certain arguments like on an object or a float or a double. We want to filter them and change the argument to a string. So we change the arguments one by one into into arguments that are appropriate. And then we fold in the mixers, which are methods that basically look at the argument and decide how long is it. Does it need special encoding? There's a length and a coder being thrown around in the slides here. The coder is this implementation detail in Java-lang string where there's a byte that says whether or not the string is Latin 1 encoded or UTF-16 encoded. So that one needs to be kept in memory and calculated. So the mixers, once they are done, produce something that is you have a known length and you know which coder to use for the string. Using that length, we create an array, a byte array that we are then prepending the strings and other arguments into. Then we throw away the arguments and we do a new string on the now fully fleshed out byte array. So this is a very one way to visualize this is through an expression tree. Each method handle invoke at the edge creates the filters or does the filter and such. But the thing is, every time we do one of these transforms on a method handle, it creates an intermediate class. So there are lambda forms that are built up to implement the method handle shape or the method handle, and these classes are being spun up pretty eagerly. But then we transform that method handle into a new class. We get a new into a new form. We get a new backing class and such. So each transform step potentially generates a class, and when we have loops over many arguments, we might get tens or scores of classes being generated just for a single complex concatenation shape. And that's a little bit at the core of the startup footprint issues we've had in this space. To just translate all that convoluted nonsense into Java code, this is a method that was in the JDK until recently to concatenate two objects with each other. It follows the same principle, taking the stringifiers or string off the initial coder, mixing the values together, and creating the array prepending arguments. For performance reasons, it was chosen to prepend from the end of the array. This saves a little bit on certain primitive arguments like integers, where we don't have to calculate the string size twice or keep the string size in memory. So this is like the simple rundown of what the current string concat factory is producing. And then I mentioned that high-arity fallback, and since the method handle typically performs well, but as it grows, it becomes unwieldy for the JIT compiler. We had to work around by reinstating a simpler strategy that was part of the JDK 9 implementation as a selectable strategy. But now we have this solution where rather than selecting wholesale, switching from the default pretty optimized strategy to this fallback, we have this high-arity threshold parameter instead, which is by default set to 20. So any unwieldy large expression will now generate code or generate a class and forego the method handle expression framework. This generates and install hidden classes alongside the class of the concatenation expression, nothing really magic to the code generator. We create basically the same sequence, the string builder, append chain, as Java-C would do for a Java 8 release target. So that's a quick rundown of the current state of the string concat factory implementation. But I wouldn't be here if it wasn't for performance. And let's look at the current performance characteristics of string concat since YEP 280 got in line. And now after this high-arity fallback was reinstated. So this is just a micro benchmark for numbers from a micro benchmark that tests various concatenations of various arities from 123 arguments at the top, and then down to larger selection of small arity concatenations. From the top, you can see that there are a few that are underperforming the Java 8 style bytecode. Look at the line that says 1 for speed up, and those are all all part of this high-arity fallback mechanism. Those 123 123 arguments, though, they will run into the high-arity fallback. It doesn't terribly underperform at that arity length, but it's still a 15-20% downside. Startup numbers has been, as I mentioned, has been poor. When we introduced this in Java 9, it was worse. On a quite simple test, I blogged about this a couple of years ago, and showed that the overhead in Java 9 for a series of concatenations could be quite damning. About 100 milliseconds for a quite simple program. We got that down over the course of a couple of releases to a more manageable amount, depending on the complexity of your application. Then instead of many seconds or many hundreds of milliseconds in later releases, it will be down to an integer factor speed up, at least, of that initial overhead. And to do that, we did a lot of heroics, as a colleague of mine expressed it. We took the expression tree, we massaged it into combining the logical length encoder that was, logically they are an int and a byte. But if we combine those into a long, we need fewer method handle transforms to implement the same thing. And that's great, because with fewer transforms, we generate fewer classes and all that. But the logic of the code becomes a little bit murkier. But yeah, it definitely had like an integer factor improvement in reducing the number of classes generated. We refactored so that string and objects are treated the same. That cut down the number of classes by half in many cases. We folded constants into the prepend combinators, moving them into like this little, since they are then treated on the side, the prepender is identical to the tree shape depending on whether there is a constant or not. That reduces the number of shapes by an exponential factor. Yeah, and those I'm quite proud of some of those optimizations, since they at the time really helped us, remove a lot of the overheads that we were seeing. But especially on when you scale things up, the impact of those in accumulation had quite an impactful. So I'm going to come back to this test a little bit later, but if we enumerate all the possible expressions and do string concats over them, like every argument, every argument is an object, every argument, and then permutate with all the other basic arguments that affect the shape. Then in Java 11 we could on this test just for 4 arity expressions we ended up with about 40,000 generated classes, and with these optimizations to reduce the tree shape, we got that down to around 3,000 classes. But still, with a 92% reduction in classes on this example, we still had lingering woes. We see this pop up in every application where people are bemoaning startup in Java. We see people are finding out about this hidden Java C flag to emit Java 8 bytecode instead of running the startup through the and such. And then people have been asking for, like, why did we remove the string builder strategy that we now have put in place again for as a workaround on large arity? Because if we would use that wholesale on any expression, that kind of strategy can at the extreme end generate an extreme number of classes. And this on this stress test, that simple strategy that you can now yet again activate across the board with the high-arity threshold equals 0 flag that came in with JDK 23. We see that that generates an exorbitant number of classes, one for every string concat expression. So if you have 320,000 string concats, you will get 320,000 classes. And this test that runs in 10 seconds on most of the baselines now runs in 200 seconds. So the workaround works nicely for high-arity expressions to solve that yet issue. But now we're looking for solutions and to a couple of problems to kind of marry these solutions. Get something that has both low class generation count, good performance, and good startup. So question is, would Leyden come to the rescue in this regard? So Joy Lam and others are going to talk at length about Project Leyden later during this conference. But I'm going to just do a quick guest mention here that with Leyden we can pre-resolve string concatenations, and we doing this requires a training run, but this then collects, generates, and archives the code behind the generated call signs. And string concat heavy startup tests can see 4 to 5 times speed up with pre-main, or 80% reduction in overhead. And this includes the full VM bootstrap. So the relative overhead of string concatenation is basically down more than 90%, probably. So that's super promising. So the question is, are we done here? But never. I mean, I wouldn't admit defeat that easily. Leyden is not a rug to sweep things under. The Leyden cache, while great, is only representative of its training. Once we get outside of, if you run into string concats that Leyden hasn't captured, you would get a little bit of you just defer this startup bump to somewhere later in the program. That might be even worse in some regards. Not every app will be able to pick up Leyden. We shouldn't, just because we have an expert tool to solve specific issues, we should mind making sure that Java is great and runs great for any application, whether or not with Leyden or other techniques to speed up startup. And since the Leyden implementation just pre-resolves the exact same class as generated by string concat factory, we will the code that is archived will have any of the same performance characteristics and JIT issues that regular Java or a regular execution of a program would. So there's still motivation, I think, to clean this up, and cleaning up is always good. So my idea was to basically keep poking at that hidden class generation that we already do for the workaround implementation, and JEP 371, I forget which, JDK 15 provides this mechanism to generate and load classes that are not into any module or package or whatever. If you have the right privileges, allows for those classes then to access private internal implementation details. And funnily enough, the JEP even mentions string concat factory as a candidate for what this feature is to be used for. It says plainly in the JEP that string concat factory could generate hidden classes to hold the constant concatenation methods. I don't know what the constant concatenation methods is, but let's do that. So general idea would be to spin a class that holds constants and instantiate that at each call site. Pre-compute whatever is possible in the constructor and lean on being defined in Java lang. More or less what the method handle expression tree is already doing from the string concat factory. We pre-calculate at the bootstrap time, which initial length, which initial code based on the constants and all that. So we put that in a constructor, allocate that object, and have do concat or whatever method to take the arguments, that is like the arguments for the concatenation. So for this example, for a concatenation of any prefix with any foo object argument and a bar int argument, we would generate code that kind of just calls into these string concat helper methods to do the stringification, calls into the coder method of the string to calculate the coder. Should be byte, not int. And then mix in the lengths, basically the same sequence of, or same code that would be produced by the method handle translation. For experimentation purposes, it's always good to keep things as similar as possible when you're doing a prototype, right? But that's not enough to get all the way, because if you're just generating classes, we run into that one class per generation. So we need a little bit of a caching mechanism, and since this cache is going to be in string concat factory or thereabout, we need to make sure that we erase arguments, don't leak user visible classes or types into the argument, and then cache that in a way that doesn't preclude class unloading into. So we, I think it was Jim Lasky who wrote the reference key map caching mechanism. So pretty nice little tool that is currently JDK internal to keep weak or soft references on whatever we're keying on, the method type in this case, and then having a soft reference to our pair of constructor and the concatenator. So we're creating two different method handles: one for the constructor, taking the constant arguments, and one for the static concat method handle. We cache those so that whenever we see a similar method shape in the string concat factory, we could try and see if we have already generated the class for this, and reuse those handles, create an instance of the concatenator, and return that handle. So that's the plan. And I started working on this at the beginning of the month. Then I had to take a vacation. But before I went on vacation, I realized that just preparing the groundworks for this prototype, I would not like to do a couple of cleanups to the existing implementation. I managed to by simply simplifying some shapes and avoiding moving some shift operations around a little bit, we could actually get a quite nice little speed up to the string concat baseline, which is great. Even though we're aiming to replace it by simplifying the code that we generate, that would make the target of my prototype easier. So then I mentioned this because this led to an engineer at Alibaba, Xiaojin Zhen, to go out, keep going out on that tangent. I commented that, hey, I just optimized this because I wanted to simplify this stuff, and he kept rolling that ball down the hill, and I had to tell him about my prototype work I'm doing. So in July 20, I mentioned in a PR that he did to keep on optimizing here that I have this prototype idea. I have some of the code written and such. And I think he only heard half of what I said, because the day after he sent me a PR with the code that I was planning to prototype. This prototype, which I now have to say, well, it's mainly Xiaojin's code, but me and Chen Yang and others have guided Xiaojin to pick up, make sure to have the all aspects of the prototype idea. I sent him a few PRs into his PR, as one does on GitHub, to implement the caching and make sure that not run into this one class per concatenation trap that we wanted to avoid. And yeah, it's great, because I was mostly on summer vacation and didn't really have that much time to work on this. So and ended up with a prototype here that does what I was setting out to do. Use the class file API to spin hidden classes, cache, put them in the cache, making sure that they can be. So we ended up with there's the example tidbit of the how to use the class file API. You just define some concatenation. So we prototyped quite a lot, experimented with putting everything, moving so much as possible to a shared base class and the string concat base class, and then now we're at the point where we're micro optimizing this, splitting apart the concat code into a method to calculate length and a method to do all the prepends, because that just sits more nicely with the JIT. Moving whether or not we need to calculate the coder into an optional method, because depending on the shape, if there are no methods that can be changing the state of whether or not something is Latin 1 or UTF-8, UTF-16. For example, an integer will never mutate the coder. Then for a certain class of concatenations, we don't need that coder method. That's great. That kind of optimizations we couldn't really do with the method handle implementation. So we're already at the point where we're kind of optimizing away from the baseline. I mentioned this is a duplicate slide. Startup numbers, while not as dramatic as the Leyden showing, we do on a similar benchmark do get a 40% reduction in overhead. We have the number of classes generated on this particular test. It all depends on how you set up your test. I have one test that just does one string concatenation with 100 arguments, and that will generate about 160 classes in the baseline. And with this, it generates one class. So that's a little bit of an improvement, I think. And for a prototype, this is very close to being on par with the complex method handle based or method handle expression baseline. So we have a couple of regressions, outliers to look into. Might be measurement errors. I haven't been able to do as thorough benchmarking on this as I would like before integration, but for a talk, who cares? We see some speed ups, some slowdowns. I would characterize this as being mostly neutral around the 1x speed up, which is kind of what we expect. We don't expect to be better than the baseline implementation for throughput for this. We just want to make sure that parity in performance on throughput, but nicer story for startup and getting there. And yeah, overall, it's pretty nice. We have some open issues, like on that exhaustive 4-arity stress test, we generate about twice the amount of classes. One likely reason of this is that we are generating one class per permutation of object int, long, char, boolean, and float and double, whereas the baseline kind of treats float and double specially and generates one core class for those. So that's one point where the baseline is slightly better on number of classes generated, but it's not better on time. So we're beating it on time, but it's generating slightly more classes on some corner cases. So maybe we can do a hybrid approach where we do the stringification of floats and strings the same way as we've done in the past, and get to a point where we are on par even on that test. Otherwise, the general open questions when it comes to a big PR, we need to develop tests to ensure that unloading of these unreferenced concatenation classes works as expected, and do thorough testing and validation on a wider range of tests, benchmark, and applications. But overall, I think this work is surprisingly close to completion, very much thanks to Xiaoyin Wen at Alibaba, who's not here. Yeah, how are we for time? 5 minutes? 5 minutes, yeah. So I'll just quickly look at what to take away from this. Method handles are still great, but maybe we can do less of them and aim for a low glue to code ratio. Characterizing method handles as glue and code as the things that we are gluing together. It's good if the base building blocks are as aren't these very tiny things, but more of good chunks. Hidden classes, they're a relatively new thing, and I love them. we can do anything that we can do with method handles. We can do with hidden classes. Generating code, injecting them into wherever we need them, with direct access to private implementation details. You can use them. You can tie, depending on what your needs are. You can do strong or non-strong. You can use them, put them into nest and nestmate access-based control, for example. So it's very flexible and nice, and allows for the JDK and also frameworks to generate code that gives access to private implementation details, that allows library authors to hide away implementation details much better. And the new class file API, which is currently still in preview, but we use it internally for Lambda code generation, proxy generation, and such, is also pretty cool. The JDK has already been transitioning to use this API consistently in places. Before, no hard feelings to ASM, but getting rid of third-party dependency and also an array of custom code generators. We had these proxy code generators and such that now can consolidate on one single API. That's pretty nice. Just a quick note that there are startup overheads to the class file API, and we're looking at those. There's some optimization in progress. Running out of time, but future work. Highest on my list is to remove the method handle-based implementation, clean up and remove some of the method handle transform that was added only for optimizing string concat. They probably don't make any sense. We never made them public because we didn't know if they were, more generally useful. Now probably they don't make the cut for being included in the public API. So let's clean up a little bit there. We can look forward to any reintroduction of the string template work with more with a warmer, fussier feeling that is can reuse the same thing that String Concat Factory is doing, because we're lowering the cost of it. And as we lower the cost of applying String Concat Factory style optimization, it might become more appealing to use in more places. Xiaojin already has PRs sent out to do something with datetime format, and I haven't been able to review it. But yeah, we can look at those kind of bootstraps and optimizations later. And we can also maybe look at specializing more on demand when it really makes sense. We can. We haven't really gotten around to this promise of JEP 280, but maybe someday. Right. I'd like to send my thanks to Xiaojin for making my prototype and doing great work, and to Chen Liang for helping out with the slides, and also Victor Klang and Joe Darcy helped me review this talk. So I think we're up for time. I guess 2 minutes. Oh, Remy. Did I say something bad about ASM?
No, it's not about ASM. I think I have more work for you, which is now that we start to have Valhalla. And in Valhalla, you can have value class to represent primitives. You may be able to share more code, which is instead of using an int or long, you can use integer and Java long directly and share more shapes.
Yeah, it sounds reasonable that those classes should be shareable across different. Would you want to comment on that, Shem?
Sure. So I'll just answer the question. So in the current Valhalla prototype, we are distinguishing nullable integer and the non-null integer, and only non-null integer will be able to share like the primitive ints routine, and because string concatenation requires nullable objects to print the null literal when the reference is null. So there will be a little bit of difference still.
Okay. Mr. Charlie Oliver Nutter.
This is fun stuff. I got a similar optimization in JRuby for Ruby's string concatenation. And I started at the end, and I'm working my way back to see how much of the beginning part ends up being useful, the more complex method to handle expressions, just to see if it inlines better, optimizes better than my simpler version. I'm wondering, is there anything in any of these implementations that profiles the size to try and guess the buffer size for future string concatenations? That's been one that's a challenge for me, is that ideally, if I'm appending 5 dynamic elements and it works out to be, 60 bytes all the time, I'd like to allocate a buffer that's at least long enough to hold those right at the beginning. But profiling that so that I don't all of a sudden have an outlier that makes me allocate tens of thousands of bytes when I don't need them.
Right. So while there has been implementations that are inexact and cannot do an estimation, all the strategies we have for string concat factory in the EDK today are exact. They do calculate it precisely the size of the byte array that is needed to accommodate. Well, one drawback of that is that we are stringifying all the input arguments early, so we're turning everything into strings. I'm not sure how Ruby, if and that like one of the aspects where really like specializing might be possible is to if you have a class of objects where you don't really want it too stringy, but you have a way to stream that string representation into a byte array directly yourself, then that would be some point to kind of extend and optimize. But today we calculate exactly.
Right. Yeah. So basically, all of the JRuby. I don't know if this is always working here. All of the objects that come in for a JRuby are dynamically. They're all Ruby object, but we do look for certain types that can append themselves into the buffer. But what I'm more interested in is when you have those dynamic elements that have to stringify themselves. I would like to profile and guess ahead of time, based on previous runs, whether I can make a buffer wide enough so I don't have to reallocate halfway through.
Yeah, sorry, it's a bit out of scope for my knowledge. So yeah, I can't give you a good answer now.
Hey, I'm wondering what you think about the general implications for method handle. Is it that method handles are just not appropriate to this sort of task? Is there something that method handles implementation could be doing better? Is there a way to make method handles able to do something that performs as well as what you've got?
I would have to qualify that it very much depends on the complexity of your code, and the string concat expression tree works very well. It's just that it kind of an extreme end when it gets quite unwieldy, that we ran into issues that we would like to now tease our way out of. So I would say for most purposes, most applications or most applications of method hands probably wouldn't run into that kind of thing. But it very much depends on if you're doing this over for something that can be hundreds of arguments long. then perhaps you need to think about making larger chunks, like we've now prototyped for string concat. So it all depends, but just make sure that once you get to hundreds of method handles string together, you're gonna start having growing pains on the both getting lots of waste with the intermediate classes that you don't really need and JIT overheads because the expressions become too much.
Just to answer to your question, just a quick answer is usually what I've found is that if you have more than a certain number of parameters, it may be worth to box everything in an array of objects and use always the same representation for that, instead of trying to generate an ungodly amount of method handles.
Yeah, I think that concludes the Q&A session.